Okay, let me start. Today we are going to talk about the characteristic equation. Actually, this chapter related to the eigenvectors and eigenvalue that we discussed the last week, right? So actually, this is the chapter 5 in our textbook. So okay, so before starting, let's recap the eigenvectors and eigenvalue. Okay, so this is the lecture 13.1. So what was the eigenvector, eigenvalue? As you can see here, so if we have some kind of transformation A and we want to transform the arbitrary vector in the input space, then each input vector will be transformed to the output vector, something like this, right? But there are some vector that has the same direction but only have the magnitude difference before and after transformation. So in this case, this vector is called the eigenvector, and each corresponding the magnitude is called the eigenvalues, right? So if we know the eigenvectors, eigenvalues of the transformation A, then we can understand the shape of the shape after applying this transformation A, right? So this is the eigenvectors, eigenvalues in high level intuition. So yeah, formally eigenvectors is the non-zero vector x such that ax is equal to lambda x for the scalar lambda, and the scalar lambda is called the eigenvalues of the matrix A if there is the non-trivial solution of x of the ax equals lambda x. Such an x is called the eigenvectors corresponding to lambda. So when you see this function, this equation, if x is equal to 0, that will satisfy this equation, right? So it will be the trivial solution as x equals 0, but we want to find the non-trivial solution when x is not equal to 0. So in this case, it will be the eigenvectors and eigenvalue. So when we reformulate this equation, something like this, then we can say that the lambda is the eigenvalues of the matrix A when this equation has a non-trivial solution. This equation has a non-trivial solution. So in this case, the set of the whole solution of this equation is just the null space of the matrix A minus lambda I, right? So this whole possible solution set is a subspace, and it is called the eigenspace. Okay, so in other words, the eigenspace means the set of the possible solution of this equation. So yeah, so we can easily find out the eigenspace by solving this equation, something like this, right? Using some kind of the row operation technique to find out solution. So if we find out general solution of this problem, it will be something like this, right? So when x2 is not equal to 0, the eigenvector will be the infinitely many possibility. So it can be 1, 1, 2, 2, 0, 5, 0, 5, something like this, right? Then we can extend this kind of concept to the more higher dimensional case, for example, the 3x3 case. So we can also find out this equation, the solution for this equation. So something like this, right? Yeah, so you have the basis for the eigenspace. So yeah, there was one more theorem. The eigenvalues of the triangular matrix are entries of each main diagonal. So when you think about this matrix, something like the triangular form, so in this case, the A1, A2, A3, 3 will be the eigenvalue because of this formulation, right? And what else? And yeah, there was one more theorem. So when the vector v1 through the vr the eigenvectors that correspond to distinct eigenvalues lambda 1 through the lambda r of the m by m matrix A, the set V1 through the VR is linearly independent. Linearly independent. So how can I prove this? So suppose, okay, first of all, we can suppose that this set of the vectors is linearly independent, but it's not possible. So we can say that those vectors, the set of those vectors cannot be linearly dependent. So it must linearly independent. Okay. So it was the theorem. So today we will use this kind of theorem to derive the characterization, characterization, and some diagonalization. Okay. Okay. So let's start. So yeah, before starting, there is the notification about the final exam. We will take a offline final exam. So as I mentioned previously, the date is the June 23 here, and the location of this exam is the 애기능 Student Center 31 and 301 and 302. So in Korea, 애기능 301호, 302호, and the scope of this exam is from the lecture 1 through the lecture 13. Actually, today's lecture is lecture 13, right? So we have the one more lecture in the next week, right? So no books and no note or calculator or the other electronic devices are not allowed. And please start your study as soon as possible. Okay. Okay, so let me start. So first of all, to derive the characteristic equation, we need one more invertible matrix theorem. Actually, from lecture, what's that? Lecture 4.3, maybe, yeah, 4.3, we introduced the invertible matrix theorem. So what was the invertible matrix theorem? It's a kind of the condition that the matrix A is invertible or not. So there are several kinds of the condition that A can be invertible matrix, right? So today we will add two more things. So okay, let me start. So let's say matrix A is the n by n matrix, and A is the invertible if and only, first of all, the number 0 is not an eigenvalues of A. Okay, so it means that eigenvalues of the A does not contain the number 0. Then in case A is invertible, matrix A is invertible. Then one more thing is that the determinant of the matrix A is not 0. It's not 0. So if you remember the definition of the determinant of the matrix, the determinant A, if the determinant A is not 0, A is invertible, right? There was the theorem, right? Okay, so let's go back to the last week. Yeah, we make up the properties of the determinant, right? So in here, right? So determinant A is not equal to 0, A is invertible, right? So in here, you can easily understand the determinant by using the determinant of A, we can determine matrix A is invertible or not. So today we will use this kind of theorem. Okay, so what is the characteristic equation? What is the characteristic equation? Okay, so first of all, let's think about to find the eigenvalues of this matrix. A is the 2, 3, 3, negative 6, right? First of all, what you want to do is to formulate the equation A minus lambda I times x is equal to 0, right? From here, right? So we must find whole scalar lambda such that this equation has a non-trivial solution, right? Because this is the definition of the eigenvectors, eigenvalues, right? Then how can I find the lambda such that this equation has no trivial solution? If we use the inverter matrix theorem, it is equivalent to finding whole lambda such that matrix A minus lambda I is not invertible. So it is equivalent to finding whole lambda such that the matrix A minus lambda I is not invertible. Then how can I find the value lambda that make this matrix not invertible? There are several kinds of ways, but we will use this theorem. So we will check the determinant of this matrix. So determinant of the A minus lambda I is equal to determinant of the A minus lambda I. So because I identity matrix is 1 1 0 1 0, right? 1 0 0 1, right? So it will be 2 minus lambda 3 3 negative 6 minus lambda here, right? So to find the lambda that make this matrix not invertible, we will find the lambda that satisfy determinant A minus lambda I equal to 0 here. Okay, so by using the definition of the matrix, we can solve this equation, right? So you can easily find the determinant of this one. Okay, so if you can, please go back to our determinant lecture, maybe lecture 8.1 and 8.2, right? And then we can easily find out the lambda is 3 and lambda is negative 7. Okay, something like this. Okay, so in here, to find out the eigenvalues of some arbitrary matrix A, we need to find out the solution. We need to find out the solution of the equation here. If I rewrite this one again, we have to find the solution of A minus lambda I is equal to 0. Okay, so let's think about how can we do that. So this is the definition. As you can see here, the scalar equation, determinant of the A minus lambda is equal to 0 is called the characteristic equation of the matrix A. Okay. So this is the definition of the characteristic equation of the matrix A. In other words, by finding the solution of the characteristic equation of the matrix A, we can find the eigenvalues of the matrix A, right? It's very intuitive. Actually, it is related to the lecture 13.1, but today we introduced the concept of the characteristic equation to find the eigenvalues more systemical way. So in other words, the scalar lambda is the eigenvalues of the n by n matrix A if and only if the lambda is satisfy this characteristic equation. Okay, so let's do that. So by using this characteristic equation, we can find out the eigenvalues. Okay. So first of all, let's find the characteristic equation first. Okay, so let's say there is the matrix A, right? Interestingly, the matrix A has the triangular form, right? So if you remember our determinant lecture, if the matrix A is in the triangle form, we can easily find out the determinant of this matrix A, right? How can we do that? How can we do that? Okay, let's go back to the Yeah, here. No, it's not. Where is that? Yeah, here. So this is a lecture 8.2, right? So here is the, where is that? Yeah, so like this. So as you can see here, if we have the echelon form or triangular form, we can easily find out the determinant by using this constant with this fourth term, something like this, right? So it is the very useful way to find out the determinant of the triangular matrix. So in here, we can easily find out the triangular determinant of this matrix as well. So first of all, to find out the characteristic equation from the a minus lambda I. So what is a minus lambda I? Because lambda I is something like 1 0 0 0 0 1 0 0 1 0 0 0 1, something like this, right? So we can easily find out the a minus lambda I, something like this, lambda I, something like this, right? Then this matrix still the echelon form. So determinant of this matrix A will be the multiplication of this diagonal term, right? So 5 minus lambda, 3 minus lambda, 5 minus lambda, 1 minus lambda. Okay. And then the characteristic equation is the determinant A minus lambda is equal to 0, right? So because there are two terms, so 5 minus lambda squared times 3 minus lambda and 1 minus lambda is equal to 0. And we can rewrite this term something like this. Lambda minus 5 squared, lambda minus 3, and lambda minus 1 is equal to 0. Okay, so yeah, this is a characteristic equation. To find the eigenvalue, we have to find the solution of this one, right? It's very easy, right? What? Lambda is 5, lambda is 3, lambda is 1, something like this. It's very easy. And then if we expand this product, something like this, then if we extend this product, we can also write this characteristic equation in a polynomial term, something like this, right? So in here we can find out several things. The first one, the matrix A is the m by n matrix. The determinant A minus lambda I is the polynomial of degree n, which is called the characteristic polynomial of the matrix A. So this is a characteristic equation, and if we expand this one, we can say that this is the polynomial characteristic polynomial matrix A. Okay, so this is the same thing, right? And there are some concepts. First of all, the eigenvalue 5 here, eigenvalue 5 here, is said to have the multiplicity 2, right? So multiplicity 2, because the other term has only 1, but when lambda is equal to 5, it has the square term. So in this case, we say that the eigenvalue 5 is said to have the multiplicity 2, right? So in general, the multiplicity of the eigenvalue lambda is its multiplicity as a root of characteristic equation. Root of the characteristic equation here, right? So Actually, this is just the concept. We will use this concept to in the following, right? Anyway, in this example, we found the characterization using the determinant concept, right? Okay, so in this lecture, there is a one more theorem called the similarity. Similarity. What's the meaning of the similarity? What's the meaning of the similarity? Okay, so think something like this. Okay, there is the person, something like this, without any clothes, but there is someone who wearing the shorts and pants, something like this. But the face of this one looks like same. So in this case, we can say that these two people are similar, right? In Korean, 닮았다, right? So what I want to do is to, okay, let's think about this is a matrix A and this is another matrix B. Then if the matrix B is similar to the matrix A or matrix A is similar to the matrix B, then some kinds of properties of the matrix A and matrix B are same, right? So in conclusion first, if the eigenvectors and let me say again. So if matrix A and matrix B are similar, then eigenvectors and eigenvalues of the matrix A are similar as the eigenvalues and eigenvectors of the matrix A, even though two matrices are different, right? So that's why we study the concept of the similarity. Okay, so how can we define the similarity between the two arbitrary matrices? Here's the definition. Okay, so let's say we have the matrix A and matrix B in n by n space. Then matrix A is similar to the matrix B if there is an inverter matrix P, such that P inverse times matrix A times matrix P is equal to B. Or equivalently, A is equal to P times P inverse. It is just invertible, right? By using the inverse of the matrix P, we can exchange these two equations, right? So in this case, if there is the invertible matrix P that satisfies this equation, we call matrix A and matrix B is similar. So in other words, if we write the matrix Q as for the inverse of the P, we have the inverse matrix Q times B times Q is equal to A from here, right? So P is also similar to A, and we say simply that the A and B are similar. So in other words, A is similar to the B and B is similar to A, or A and B are similar. Okay, so if there is the inverter matrix, right? Okay, so this is the definition of the similarity between two matrices, right? So in this case, the changing original matrix A into the similar matrix as a P inverse of the P times A times P is equal to similarity transformation. In other words, replacing the original matrix A as a similar matrix P, or the P inverse times A times P is called the similarity transformation. Okay, so actually by using this concept, we will derive the diagonalization of the matrix A. So which is the kind of the matrix transformation. So which will be discussed the next lecture. Anyway, this is definition of the similarity and similarity transformation. And as I mentioned previously here, okay, so if the n by n matrices A and B are similar and they have the same characteristic polynomial and the same eigenvalues with the same multiplicities. What was the multiplicity? Here, right? The factors of the square, right? Factors of the root, right? Then let's prove this one. So let's prove this one. First of all, if matrix A and matrix B are similar, we can represent the B is equal to the inverse P times A times P, right? Then to find out the characteristic equation, we can write the B minus lambda I here. Then P is equal to here minus lambda I equal to here. But we can decompose the I into the P inverse P, right? It's very easy, right? Then by extracting the P inverse here and here, subtract this, there remain AP minus lambda P, right? And then if we extract the P here and here, the finally inverse P times A minus lambda I times P, right? So in other words, if A and B are similar, B minus lambda I and negative inverse of the P times A minus lambda I times P is are same, right? Here and here, right? Okay. So to find the characteristic polynomial or characteristic equation, we can find out determinant of the matrix P minus lambda I here. So in this case, determinant, this one should be equivalent to each other. Then from the properties of the determinant, we can decompose this multiplication, something like determinant inverse of the matrix P and determinant A minus lambda I and determinant P, right? Right? And then we already know the determinant of the inverse P times the determinant P is equal to 1. Why? Determinant P inverse P will be the determinant I, the determinant I will be the 1, right? Why? Because the determinant I only has the 1 in diagonal without any non-zero values on non-diagonal term, right? So in this case, determinant I is the multiplication of the every diagonal, so it is just 1. Okay, so in other words, determinant B minus lambda I is equal to determinant A minus lambda I. So as you can see here, the characteristic form of a polynomial of the matrix A and matrix B are same, right? So in other words, they have a same what? Same eigenvalues. Okay? So they have the same eigenvalues. So yeah, there are some warning. First of all, matrix this one and this one are not similar, even though they have the same eigenvalues. So this one and this one might have the same eigenvalues to in some case, but they are not similar. So it means that where's that? So it means that this one is the true, but this one is not true. So even though they have the same eigenvalues, they are not similar. They might be not similar, right? And one more thing is that similarity is not the same as the row equivalent. So similarity is not the same as the row equivalent. So if A is a row equivalent to the B, we can represent B as a elementary matrix E times A, right? So if we discuss the previous lectures, by multiplying the row operation, the eigenvalues would be changed, right? So, but in the similarity transformation case, the eigenvalues will not be changed, right? So this is the what I want to let you know. So this is the concept of the similarity. Then by using this one, let's derive the matrix diagonalization. Actually, it is one of the most important concepts in this course and in the linear algebra world. So by using the eigenvector concept, we can decompose the arbitrary matrix A into the some diagonalization terms. So okay, so let's see this one.